This problem says to evaluate a permutation of 5 things taken 3 at a time times a combination of 8 things taken 2 at a time. So this is strictly just a problem to see if you can do the mechanics. Remember, you do have your Casio FX260 calculator, so you can actually do both of these on here. And that's the way that I would expect you would do it most efficiently. Remember, when you're doing these calculations, that the shift 1 key is the combination for permutations, and the shift 2 key is the combinations. So keep that in mind. When you're doing a permutation, you're going to be using shift 3, and when you're doing the combination, you're going to be using shift 2. So given that, you simply enter the 5, then shift 3. Shift 3 gives you the permutation, and then equal, and then you want to multiply, so it would be times. Then you have 8, and this is a combination, so it will be shift 2. That's the combination. Equals. And when you do that, you will get the result. So P, permutation, 5 things taken 3 at a time, times a combination of 8 things taken 2 at a time. When you do that, you will get 1,680. Now you could do each one separately and then multiply them. If you did that, I don't necessarily think that you should do it that way, but if you did do that, the permutations of 5 things taken 3 at a time would come out to be 60, and the combination of 8 things taken 2 at a time would come out to be 28, and 60 times 28 is still going to be 1680. Okay, let's look at another. Mulder will read files on 4 unsolved cases from a list of 12 cases. He does not care about the order in which he reads the files. Using the permutation or combination notation, in how many ways can he read 4 of the files? And it says do not evaluate. So this is just to see if you know how to choose whether the problem is dealing with a permutation or a combination. They're not asking you to evaluate anything. Now the important thing to notice here is it says that he does not care about the order. When you don't care about order, you know you're going to be dealing with a combination. So I'll just say this explicitly: because order does not matter, this is going to be a combination. So all they're asking you to do is say, okay, I'm taking 12 things, the 12 cases, and I'm choosing them 4 at a time. How many ways could I do that? And they did not ask you to evaluate it. In fact, they said do not evaluate. Be sure to read the directions carefully, because if they ask you not to evaluate something and you do, you'll miss the problem. So read carefully. Okay, let's look at this one. It says to the right is one of the possible modified bingo cards that satisfies the possible conditions. So they've taken a standard bingo card and made it follow a little bit different rules. It tells you that the numbers in column B have to always come between 1 and 15. The numbers in column I have to be between 16 and 27. The numbers in the column N have to be between 28 and 43. The numbers over here in the G column have to be between 44 and 57, and the numbers in the O column have to be between 58 and 75. And they want us to find out how many different O columns are possible. In other words, they're only asking us about the O column. So in reality, nothing else matters but the O column. They could ask us several questions about this bingo card, but for this particular question, the only thing we're interested in is column O. Now, they also want us to know that in bingo, the order of the numbers is important. So in other words, putting a 67 in this first spot here is different than if that 67 shows up somewhere else. So order matters. Since order matters, you're going to be looking at a permutation. So let's just say that here. Order matters. And that means you're dealing with a permutation. Well, how many things? It's pretty easy to see that you're taking 1, 2, 3, 4, 5 at a time. So this is going to be 5. But what are you choosing from? Well, look back over here. It tells you that the O column has numbers between 58 and 75. Now, I know some of you had problems with this on the earlier test, but if you say the number of numbers between 58 and 75 is 75 minus 58, 15 minus 8 is 7, borrow, you get 17. That's not right, because just think about it this way. If you want to know how many numbers are between 1 and 3 inclusive, and you say 3 minus 1, you only get 2. But there are actually 3 numbers. So it's the same thing here. If you want to know how many numbers are between 58 and 75, you can subtract, but you have to add one, just like you did up here, to get to 3. So go ahead and subtract 75 minus 58, but then you've got to add one back. And if you're in doubt at all, just actually list them all out. It'll take a minute to write out all 18, but it's better than missing it. I know on the last test, a lot of people missed that very similar question. So it's a permutation because order does matter, and you're choosing from 18 things, and you're taking them 5 at a time because there are 5 numbers that go in the O column. And again, with the calculator, you can do 18 permutation is shift 1, and then 5, and then equal. And when you do that, you will get 1,028,160. So there are 1,028,160 different O columns possible under those conditions. Okay, let's try another. Okay, this problem says from the 12 male and 7 female sales rep for an insurance company, a team of 4 men and 4 women will be selected to attend a national conference. In how many ways can that committee be formed? Now, this problem is slightly more complicated because you're choosing males and then you're choosing females. They're 2 separate things. So what you should think of is the fundamental counting principle tells you that the number of ways to choose males times the number of ways to choose the females is going to give you the total number of ways to choose a team of males and a team of females. Now, within that choice, you've got to look separately at males and females. So let's first of all just look at males. If we just look at males, there are 12. And we're going to choose 4. You're just selecting them to attend a conference. The order you choose them in doesn't matter. Since the order doesn't matter, it's going to be a combination. And you're choosing 12 males from 12 males. And from those 12 males, you're choosing 4 to go to the conference. The women, again, order doesn't matter, so it's a combination. You're just choosing them to go. It doesn't matter what order you chose them in. And this time you're choosing from the 7 females. There are only 7 females. But you're choosing 4 to go. So according to the fundamental counting principle, the product of the number of ways to choose the males and the number of ways to choose the females will give you the total number of ways to select the group of 8 people who will be going. So we just have to do that calculation. Now the combination for 12, combination 4, we'll be putting in 12. And remember, the combination is shift 2. So you would have shift 2 4 equals, and then you could do the multiplication times. And again, you can do them separately and multiply them together, but you can also do them at once. So you do 7, and again, it's a combination. So it will be shift 2, and then 4, and then equal. And when you do that, you will end up with 17,325. Now you could have done each one separately. If you just did the combination 12 choose 4, you would end up with 495. And if you just did the combination of 7 things 4 at a time, you would end up with 35. And that product would be that same 17,325 if you'd rather do it that way. Let's do another. On a biology quiz, a student must match 14 terms with their definitions, and no term can be used more than once. How many ways are there for the student to randomly guess all 14? First of all, if you're matching, order matters. Like, matching is if you had some things over in one column and you had some other things over in the other column, and you're matching one to the other. So order certainly matters. In fact, order is the only thing that's important. So that just tells you, just thinking it through, that order matters here. So you say, well, that's going to be a permutation, and it is. But you're actually taking all 14 of them. So you're taking 14 terms, whatever they are, and you're going to match them, and the order has to be just right. So you're taking all of them. So even though it is a permutation where you take every one of the things is actually a factorial. So you could just think of it as 14 factorial. And remember, on the calculator, the Casio FX260, the factorial is shift 3. So I could just do 14 shift 3. And you don't really even have to press equal here because there's no second number to enter. You just enter 14. As soon as you hit shift 3, you will get the result, and it comes out to be a huge number, 87178 291 200. if you didn't think about doing it as a factorial, you said, well, it's a combination, you're taking 14 terms, 14 at a time, you would get exactly the same answer, and you would do 14, and the permutation is shift 3. The permutation is shift 1, so you do shift 1 for the permutation, and then you'd put 14 in and hit equal, and you get exactly that same number. Again, a factorial, a permutation where you take everything, in other words, where these two numbers are the same, it's the same thing as a factorial. Let's keep going. The academic computing committee at a college consists of 5 administrators, 7 faculty, and 5 students. A 4-person subcommittee is to be formed. The chair and the vice chair of the subcommittee must be committee administrators, but the rest of the subcommittee can be composed of any of the faculty or students on the main committee. In how many ways can this subcommittee be formed? So this committee is broken into 2 pieces. So one piece, order matters. In other words, choosing the chair first and the vice chair second. If you choose the first person and they're going to be chair and the second person will be vice chair, that's different if you chose them in a different order. So that in that case, order matters. Well, if order matters, it's going to be a permutation. But the chair and vice chair have to be administrators. When you say the chair and the vice chair, that's 2 people. So you're choosing 2 people from 5 administrators, and order matters. So it's a permutation. Now the fundamental counting principle says you're going to take the number of ways to choose the chair and vice chair. Vice chair. That's one of your tasks, times the number of ways to choose the others. Well, we just said that the chair and vice chair choice is a permutation because order matters. So it's a permutation. You're choosing from the 5 administrators, and you're choosing 2 people. One's going to be the chair, one's going to be the vice chair. But when you're choosing the others, they just go on the committee. The rest of the subcommittee can be faculty or students. Well, there's 7 faculty and 5 students. That's a total of 12 people. And it doesn't matter. They're just committee members, so order doesn't matter. So that's a combination. So it's a combination. And you're choosing from the 12 people, 7 faculty or 5 students, and you're choosing, well, it's a 4-person subcommittee, so if you've already chosen the chair and vice chair, that means there are only 2 people left to choose from to go on the committee. And now that you've talked out the setup, now it's just a matter of doing the calculation. Remember, permutation is shift 1, so it will be 5 shift 1, and then put the 2 in and do equal, and then we're going to multiply, so times, and then you do combination. Now combination is shift 2, so you do 12 shift 2, and then put in a 2, and then do equal. And if you do that, you will get that product, which comes out to be 1,320. So 1,320 ways to form that committee given those conditions. Now, as before, you could do those two calculations separately. If you want to do that permutation calculation separately, you could, and you would get, if you did it that way, you'd get 20, and then you could do the combination calculations separately. And if you did the combination calculations separately, you would end up with 66, and 20 times 66 is 1320, which of course is the same answer.